Hello, welcome. Thank you guys for clicking on this YouTube video. Today we're going to be going over a few fluid mechanics phenomenons, and hopefully at the end we can come out with some learnings. So today we're going to be going over height and fluid velocity. We're going to study the way that this affects our fluids in a tank. To give some background, the summation of this fluid mechanics equation is basically telling us that as we increase the height of a tank, we should also see an increase in the initial fluid velocity of a fluid flowing out of the tank from a hole punctured somewhere along its side. For us, we will see that as we increase the height of our buckets, we will also see an increase in the initial fluid velocity. Furthermore, we learn that flow rate, which is the speed at which the fluid will actually flow out once it becomes a constant, can be manipulated by increasing the area and velocity of the fluid that's flowing out. For us, we will change the diameter of the holes that we're drilling in our buckets, which will change the area, which should increase or decrease our flow rate. To show this, we have a quick rundown of the technique, but we'll get to this in the actual video. So we'll have 6 buckets, drill bits of 2 sizes, and 3 different ladders. We're going to place these buckets on the ladders, drill holes in them, and see how quickly the water flows out. This should give us a good idea of how height is affecting our fluids. At the end of this, hopefully we can come to the significance that from the conventional water towers that service most cities in America, as we can see in the second photo, to the parts of our world most rural, it is important to understand how vital the ability to harness and control water is. Without pumps, pneumatic or motorized, many people around the world rely on simple gravity and valve size to control their flow and access to water. Thank you. Now let's get into the actual technique. All right, now we're going to have just a preliminary rundown of the physical aspects of our tools. We have our drill here, which is going to give us a 1 centimeter diameter hole on our first drill, which is going to translate to about a 0.79 squared centimeters area for our first hole. We have our measuring tape to measure our ladder heights, our buckets, and then we can show our ladders. So all the buckets are going to be 2 gallons. And our first ladder is 3 inches off the ground, a meager 3 inches. Our second one is about 2.5 feet. And our third one, with no bucket on it, we want to fill the bucket with water as we go up so it's a little safer, is 7 feet 4 inches off the ground. And now we're going to go ahead and do a time lapse of us emptying the buckets to make that process a little less cumbersome. So as you can see in this video, we are doing a time lapse of the buckets actually emptying. One thing we didn't mention is that as the water decreases in the buckets, so too will the flow rate just from the pressure, but it'll all be equalized out because we drilled the holes at the same heights on the buckets. So through this time lapse, we saw that the buckets were emptying at a quicker rate the higher the height was. And on the next slide, we'll have the calculations for how we found that. Okay, once we ran the experiment another time over, off camera with the 2 centimeter hole, we come to these outcomes, and we can see as we increase the ladder height, we also decrease the time it takes for the buckets to empty, which is an inverse increase in flow rate. And as we increase the diameter size of the second hole, we rapidly increase the flow rate of the water flowing out of the buckets. That proves that our theory from beforehand is one that is valid. One thing that I thought was interesting is when you increase the diameter size, this is a 2 centimeter hole, the flow is almost perfect, that it gives this beautiful laminar flow where it looks as if the water is not even moving.